Hello guys, in this video we'll study about discharging LR circuits. We have already discussed the transient analysis of charging LR circuits in the previous video, and therefore now coming on this discharging LR circuit. So in this situation you can see that initially in this circuit switch S1 is closed. I'm closing the switch and switch S2 is open, which means that this circuit is operative and this is dead. So there is no role of this resistance in this circuit, but inductor is being charged by this battery, and then I will open the switch S1 and will close the switch S2. Now when the inductor is completely charged, I'm writing it down that now inductor is being charged completely and it has a energy U is equal to half L I naught square, where I naught is the current flowing at this instant when this inductor is being completely charged. So I naught is that current when the inductor is completely charged and the current of the circuit is at its saturation level, and that saturated current is I naught. So you can also say that I naught is the initial current or I naught is the peak current. Okay, now what we are doing that now at t is equal to 0, switch S2 is closed and S1 is opened. So we are now closing the S2 and we are opening the switch. So we are technically removing this battery out of this circuit and we are introducing this resistance along with inductor. So now I am also redrawing the circuit again. Now this is the inductor and it is being connected with this resistance. This is L, and the current initially which is flowing in the circuit is I naught at t is equal to 0. Now we know that this is the peak current and hence it would decrease because we are studying the discharging LR circuit, and in fact we are connecting this resistance with this inductor, and resistance is that element of electrical circuit which is responsible for loss of energy. Therefore the energy would be lost in this circuit in the form of heat across the resistance, and therefore this current will decrease. So I can say that this current is decreasing current. So if this current is decreasing, then the polarity of the inductor would be in such a way such as to support this current, because the inductor would the EMF induced would oppose the decremental nature of this current, and hence it would try to increase the current. Therefore the polarity would be like that, because plus will induce more current and it will support the current. Now therefore we can say that inductor and resistance are connected in parallel, and if we apply KVL in this loop, then I can say that at any time t, in fact at any time t, the current in the circuit is equal to I, and therefore applying the KVL I can say that it is minus IR the voltage across resistance, and this is plus E, which is the magnitude of EMF induced across the inductor. It is equal to 0. So this E is equal to IR. Now we know that this E is the magnitude of EMF induced in the inductor, and hence it is L di by dt. But there would be a negative sign also, because this current is decreasing, and hence di by dt would be negative. I am writing it down that di by dt would be would be negative, as current is decreasing. So di by dt would be negative. So this di by dt has a negative sign along with it. Now di upon I is equal to R by L with a negative sign, and this is dt. And integrating and applying the limit of current from I naught to I. Initial current was I naught, and at any instant it was I. The initial time was 0, and at any instant it is t. So the integration of this is ln I, limit is from I naught to I, and this is equal to minus R by L into t. Now this is ln I upon I naught, you can understand this, and it is equal to minus R by L into t. Now taking anti-log, I upon I naught is equal to e to the power minus R by L into t, and I is equal to I naught e to the power minus t upon L upon R. Now this L upon R, as we all know, is the time constant, and hence it is minus t upon tau. But you should very carefully remember one thing, that this time constant in this charging circuit is completely different as compared to that was in the charging circuit, because you can see that at t is equal to tau, this I is equal to I naught into e to the power minus 1, and I is equal to I naught upon e. Now 1 upon e is again 0.6, in fact 0.367, it is 0.367. So I can say that I is equal to 36.7% of I naught. So this time constant can be defined as the time in which the current decreases to 36.5% of its peak value. Now you have to mark my words that I am not saying the current decreases by, I am saying that current decreases to 36.7% of its peak value. So this is the value which is achieved by the current at this time, which is also called as time constant. Now if we draw the graph, then the graph would be seen like that. This is I, and this is I naught, and this is the exponential decay. So the graph would be like that, and the time constant is this tau, and this is 0.367 of I naught. So this is the graph of discharging LR circuit, and I can say that the heat generated across the resistance is equal to half L I naught square, which was the initial energy stored in that inductor. So this was the complete analysis of discharging LR circuit, and in the next video we'll move to the problems which are based on the transient analysis of the RC circuits. Thank you.